In this video, we're going to be looking at displacement during accelerated motion, and we're going to be using the formula displacement equals initial velocity times the time plus 1/2 at squared. So we're going to start by looking at this graph of accelerated motion on a velocity time graph. So in the previous example, we looked at finding our average velocity. However, in this example, we may not know our final velocity here. And so if we don't know our final velocity, it's impossible to find the average. So we're going to instead take this shape that we have, and we're going to divide it into two. So we're going to have a rectangle and a triangle. Now, the rectangle, this is the displacement if our car did not accelerate, okay? Or if our object, I suppose. And that displacement is going to be our initial velocity times the time. The triangle, this is our displacement from the acceleration alone. And the area of a triangle is the base times the height over 2 typically, but again, we don't necessarily know the height. So we're going to take this formula and we're going to work with it a little bit more. So our formula for the area, so our displacement in this area is going to be the base, which is our time, times our height. In this case, our height is VF minus VI divided by 2. Now, unfortunately, we don't know VF. However, VF minus VI, we can actually solve for from our acceleration problem. So acceleration is going to equal VF minus VI over time. So that tells us that VF minus VI is equal to acceleration times time. So we're going to take this that we've just rearranged for, and we're going to sub that into our formula. So we're going to have the displacement in this part is equal to acceleration times time over 2. Or we can write this as 1/2 acceleration times the time squared. So we can put these two formulas together into our new formula, which is the displacement is going to equal the area of our rectangle, which is VIT, plus the area of our triangle, which is 1/2 AT squared. And we're going to use this formula when we don't know the final velocity, but we do know the acceleration. So we're going to do this on our next graph, our next example. So a ball is thrown upward with an initial velocity of 10 meters per second up. Okay, this is our VI. And then it asks us, determine the displacement of the ball after 5 seconds. Now that's our time. We're not given acceleration in this problem, but we know that the ball is thrown upwards, and so acceleration is going to be due to gravity. And acceleration due to gravity is always 9.81 meters per second squared down. So when we list our information, VI is going to be 10.0 meters per second up, and we're going to make up a positive direction. So we're just going to write this as positive 10 meters per second. Our acceleration is 9.81 meters per second squared down. So if up is positive, its opposite down must be negative. So we're going to write this as negative 9.81 meters per second squared. And the time of this acceleration, we're going to take 0.50 seconds. We have the same time units and the same distance units on all of our values, so we can plug this directly into our formula. So displacement is initial velocity times time plus 1/2 acceleration times time squared. All right, so our initial velocity is 10 meters per second, and that's accelerating for 5 seconds, or 0.5 seconds. Our acceleration here is 9.81 meters per second squared. The negative is very important. Otherwise, it's going to look like our ball is speeding up instead of slowing down as it gets higher in the sky. 0.50 seconds squared. And so 10 times 0.5 equals equals 5.0 meters. And here, meters per second times seconds, our seconds are going to cancel. And then 1/2 of 9.81 times 0.5, this is going to be negative 1.23 meters. And again, squared, the second squared will cancel there. So we have 5 plus negative 1.23, and that's going to give us a total displacement of 3.77 meters in the upward direction.